Hello everyone, my name is Rachel King, and the topic of this presentation is mediation, and is a Teach 1 as part of HAP 823 at George Mason University, taught by Dr. Farrokh Alemi. The objectives of this assignment are to create a counterfactual model of a dataset, and to estimate mediation effect in real and counterfactual models. Before we get into the material, I'd like to point out that there are many steps to solving the problem and several ways to organize those steps. So I recommend looking over the steps and thinking about what works best for you. The assignment is to use lasso regressions to create the network of symptoms in COVID-19 diagnosis. Remove equations that explain less than 10% of variation in the response variables. Remove coefficients where the absolute value of coefficients are equal to or less than 0.05. Remove cycles, though none should exist if you're only regressing on variables preceding the response variable. In Part A, we need to find the order of occurrence of the symptoms, age, gender, and results of the COVID-19 laboratory tests. The temporal order of the symptoms, demographic variables, and outcome was provided in the diagram shown here. Part B asks us to find the direct predictors of COVID-19 laboratory test results. Direct predictors are any variables in the regression that have a coefficient of greater than or equal to 0.05. We'll also need to report the intercept and McFadden R-squared values. The first step is to prepare the data for analysis. Import the appropriate libraries and load the dataset. Check for null values, the data shape, and identify any information in the data frame that may be extraneous. In this case, the dataset included columns of symptom occurrence and columns not found in the temporal order of symptoms. All of these were removed. Part B, Step 2, is to lasso regress the outcome variable on the predictor variables. The alpha value that appropriately constrained this dataset was found to be 0.004. You want to make sure that you're taking the absolute value of the coefficients, since relationship magnitude is important. You'll also need to print the intercept and McFadden R-squared value for later calculations and understanding goodness of fit. Remember, coefficient results of greater than or equal to 0.05 are direct predictors of the outcome variable. Also note that the McFadden R-squared value should be greater than or equal to 0.10. Using the same code structure on the previous slide, lasso regress all predictors in the temporal order only on the variables which precede them in order of occurrence. For example, after regressing the outcome variable, move to the previous predictor, in this case excessive sweating, and regress on all symptoms and demographic variables that occur before it in the temporal order in question 1A. Continue this process until you reach a regression without predictors. Shivering was the last variable in my chain of regressions, and as you can see, only age and gender precede it. Neither age nor gender were significant predictors of shivering, and the McFadden R-squared value was found to be insignificant. Therefore, age and gender drop from the model. Once we complete the regressions, the network can be built. I worked from the outcome variable backwards. For each regression, I built the nodes of the significant coefficients, and since the significant coefficients are direct predictors of the outcome, I placed an arc from the predictor to the outcome variable of the regression. Next, using the regressions, we create the coefficient matrix. You will need to report the significant coefficients, the intercept, and the McFadden R-squared value for each regression. I have grayed boxes for combinations of variables where a regression was not performed due to temporal order. Regressing based on temporal order prevents cycles in the model. To read the coefficient matrix, the variables in the column on the left are predictors in the model. The variables across the top row are model outcome variables. In this example, fever is a predictor of positive COVID test, and the arc in the model would be drawn from the fever node to the test positive node. Next, we estimate the parameters of the network. We do this by using the information from the coefficient matrix to calculate the probabilities of each possible variable combination. First, build a factorial design table to stratify the possible combinations. Each variable has a binary outcome, so for test positive, there are 2 to the power of 8 combinations, which is 256 total probabilities to calculate. Then use the adjustment formula to calculate the probabilities. In the formula, beta sub 0 is the y-intercept, beta sub 1 is the factor value, and c sub 1 is the coefficient for the variable. You're going to do this for all predictors of y. I made a separate sheet in the Excel workbook for each variable. I recommend creating the formula in Excel and applying it to all rows instead of trying to type it for each combination. Once we have all the probabilities, you build the network tables in Netica. You calculated the probability of y being 1, so the probabilities will be put into the yes column. You do not need to calculate and type 1 minus p for no. Just enter the yes probabilities and Netica will calculate the no probabilities for you. You will build all the node tables this way. When your tables are finished, the result will be the best network fit for the data, and you will have found the joint probability of COVID-19 positive test results if we don't know which symptoms were present. To find the Markov blankets, you can use regression or look at the parents in the network you built in Netica. You want to regress the outcome variable on all predictor variables. The significant coefficients are the parents in the Markov blanket. This is an example for fever. To calculate the unconfounded effect of fever on probability of a positive COVID-19 diagnosis, you first stratify the direct predictors of fever. There are 2, so there are possible 4 total combinations. You will need to use Netica to manipulate the variables. In Netica, fix the predictors according to the strata. This example demonstrates the 4th stratum, where loss of taste and fatigue are both 0. Once the predictors are fixed, manipulate fever and take note of the change in COVID-19 positive test. Subtract the values of the change observed in COVID-19 diagnosis and record this as change in COVID. The unconfounded impact of fever on COVID is the average of the change in COVID diagnosis across all strata. Since we found the direct predictors of chills in Part G, for this regression, you want to regress chills on all variables found in Part G except fever. To create a counterfactual network where fever is not mediated by chills, remove the arc in the network. You'll have to recompile the network when you remove the arc. Click the lightning bolt so the probabilities are updated. To understand the mediated impact of fever on COVID-19 through chills, we need to examine the stratified real and counterfactual models side by side. In this case, we will monitor and record the change in probability of fever for each stratum. We also need to know the frequency of the covariates in the dataset. And we will also need to know the strata frequency, which is calculated by multiplying covariate frequencies according to presence or absence in the strata. For stratum 2, fatigue is present and loss of taste is not. Stratum probability is calculated by multiplying 0.098 times 1 minus 0.028. To calculate change in COVID, we multiply the change in probability by the strata frequency and sum all the stratum. To calculate chill-mediated, subtract the change in COVID results for counterfactual and real models. And percent-mediated is calculated by dividing chill-mediated by change in COVID in the counterfactual model.